Hello, my name is Jason Bard, and I'm presenting a project titled Creating a Mini Brain to Replicate RS fMRI Time Series in ASD Patients. This is actually an expansion of my project from last year, in which I analyzed the orbitofrontal cortex of autistic and healthy patients to see if there were any marked differences we could spot in their time series, which came up with inconclusive results. Now, autism can likely be characterized as when a person has difficulty socializing with other people or has repetitive behaviors and interests. And it also helps that my interest turned out to be algebra. It is not yet known what exactly goes on in a brain with ASD, but there have been thousands of studies over the previous decades related to this topic, most often involving individual regions of the brain. Now, aside from the typical allotments into hemispheres and lobes, another segmentation involves demarcating regions in the cerebral cortex, or the outer layer of the brain known as the cortical regions, and the subcortical regions within the deeper structures of the brain. The Harvard-Oxford cortical and subcortical max probability atlases divide the brain further into several dozen distinct regional approximations, not including background noise, based on the mean volumes of brains within a study. I've highlighted these atlases in particular in Figure 1. Each of these individual regions of the brain has a volume represented as the number of voxels in which one of these regions has the maximum probability of appearing given any patient's individual brain makeup. Each region then takes up a percentage of the brain's total volume, which is referred to as the relative volume of that region. In addition, resting state functional MRI, or RSFMRI, data was taken for each patient using these atlases, and as you can see in Figure 2, one patient's orbitofrontal cortex time series was graphed. In this project, I took the relative volume of each region of the brain and used it to determine the approximate number of nodes that occurred in the bottleneck of each of a number of autoencoder neural networks, or AEs. These networks are a subcategory of fully connected multilayer perceptrons, or MLPs, in which the target, which the network is supposed to predict, is the same as the input. I then used a scaling factor to keep the number of neurons within the autoencoders comparable to their relative size. Then I trained each of the autoencoders separately on the subsets of autistic and healthy control patients and compared which scaling factor would give the lowest mean squared error loss for each subgroup. An interesting result I observed while doing this project is that the mean squared error, or MSE, loss seemed to be the same for every brain region, no matter how many neurons were in its corresponding autoencoder. That may be interesting to look into, but that may be chalked up to not training the network enough or needing some other variation within it. Another result I noticed was that the MSE loss was almost always lower for the healthy control group than it was for the autistic group. This could also be a result of how the problem was formatted, but further analysis may probably also be needed to explain why that's the case. As for Figure 3, this is what I have so far, and it shows that the inferior temporal gyrus seems to have the least amount of loss for both groups, along with some low losses in some other regions, such as the subcallosal, temporal fusiform, orbitofrontal, puneal, and cerebral cortices, as well as the cerebral white matter taken all together. In the potential future, we will deal with connecting these networks together with an intermediary related to predicting the phenotypic data of the patients, such as age, sex, handedness, and IQ, and possibly even graphically analyzing the weight matrix of the networks themselves using a Python package known as NetworkX. I'd like to thank Dr. Pedro Maya for his contributions to this project, and I'd also like to thank Dr. Jonathan Bard, my father, from Baylor Scott and White, for additional information on the anatomy of the brain and advice on neurology in general. Thank you.